Okay, guys, so here's the problem from today, all right? The question reads, a sample containing C, H, and O, carbon, hydrogen, and oxygen, having a mass of 0.5438 grams was burned in pure oxygen to yield 1.039 grams of CO2 and 0.6369 grams of water were obtained, okay? What is the empirical and molecular formula of the compound if the molar mass is 138.144 grams per mole? Okay. Let me just, to yield, we don't need this part here. Must have missed it. Okay, so feel free, guys. I'm gonna go ahead and do this problem step by step. I'm gonna take it a little bit slower, just because, you know, when we were rushing in class a little bit, I think I made a small mathematical error somewhere. The process was still correct, but you know, I think I added an extra zero here and there or flipped some numbers. So I want to make sure that we get the right answer and you guys are getting it step by step. Okay, so here's what we have. Okay, we have 1.039 grams of CO2 and we have 0.6369 grams of water. Now, the question already tells you that the compound in question here has to contain C, has to contain H, and it has to contain O. So we need these three elements to find the empirical formula. And in order to do that, we're going to have to use a little bit of stoichiometry to make sure that we're able to figure this out. Okay, so how do we start this problem? All right, well, let's begin with what we know. We know that we have 1.039 grams of CO2, okay? And we know that we have 0.6369 grams of water, okay? Now, because these compounds both contain carbon and hydrogen, two of the elements that we need, and oxygen, right? We need to figure out a way to determine the amount of carbon and hydrogen in these compounds, okay? Then we can get oxygen. So let's start by doing the obvious, is we're gonna take this and we're gonna convert this to moles, right? Now, why am I converting to moles? I'm converting to moles because I know that I'm going to use a mole ratio. And in order for me to use a mole ratio, right, I have to have moles. So I'm gonna use the molar mass, 44.01 CO2, right? That's the molar mass of CO2. And I'm gonna convert this quantity to moles. Okay, so I'm gonna multiply straight across the top. I'm gonna end, well, first off, these guys are gonna cancel here. Okay, I'm gonna end up with 1.039 grams CO2 divided by a now unitless 44.01. Okay, if I divide those out, I should end up with 0.023608. Okay, moles of CO2. If I do the same thing for water here, put this over 1, I know that 1 mole of water has a mass of 18.02 grams water. All right. So if I multiply straight across, remember that these guys cancel. If I multiply straight across, I'm going to end up with 0.6369 moles of water. And I'm going to divide that by a now unitless 18.02, right? If I do that division, 0.6369, divide that by 18.02, I should end up at 0.035 344 moles of H2O. Okay. So we have our moles of H2O. So what comes next? Well, now that we know our moles, now I can use each individual compound to determine of those moles, for example, of the 0.023608 moles of CO2, how many of those are carbon, right? How many of those are carbon? How many moles of carbon are present? So just to kind of break it up here a little bit. So we're going to take our moles of carbon, 0.023608 moles of carbon. Okay, and I'm going to multiply it by the mole ratio. I know of CO2, sorry. I know that 1 mole, right, of the compound CO2 contains 1 mole of carbon, right? Now, where do I get this from? Well, if you take a look at CO2, here we have 1 mole of carbon and we have 2 moles of oxygen, right? So this is exactly what's going on here, okay? We're just putting it into the terms of a fraction. Now, I'm not doing 1/2 here because I'm not looking for oxygen. I'm only interested in how many moles of carbon there are, okay? So because I'm only interested in the 1 moles of carbon, I'm focusing right here, right? I know that 1 mole of carbon exists in 1 mole of CO2. So if I set it up like this, it's a 1-to-1 ratio, so I should end up with the exact same number. And that's exactly what happens. Moles of carbon in 1 mole of CO2. Well, in those many moles of CO2, right? Okay. All right. So there's carbon. Now let's do oxygen. Oxygen is going to be the same process. Okay. Oxygen, we'll use a different color here. Probably should have reversed those, but that's okay. Okay, so now we're looking for water, right? And hydrogen. Sorry, I kept saying oxygen. So we have 0.35344 moles of H2O. Okay. Now I know that in 1 mole of H2O, right? 1 mole of H2O, there are 2 moles of hydrogen, right? And this goes the same thing to the mole-to-mole ratio, right? H2O has 2 moles of hydrogen to 1 mole of oxygen. If I was looking for oxygen, I'd be using this one, but I'm not. I'm looking for hydrogen, so I'm using that one, okay? I know that 1 mole of H2O contains 2 moles of hydrogen. So what I'm going to do is I'm going to multiply straight across. See, this is where I made the mistake earlier. 0.03544, okay, times 2 is going to give me 0.07068 moles of hydrogen. Okay, so working this problem out, here's what I've determined, right? In the 2 products that were formed, CO2 and water, I have produced in those compounds 0.0236 moles of carbon and 0.0706 moles of hydrogen. Okay. Now, moles are great, and we're going to use them a lot. But now that we have the moles, we have to transition. We have to take these into grams, right? Because we need to be able to measure these things. So what we're going to do now is we're going to take the moles, right? We're going to take the moles and we're going to go to grams. And I'll show you why in just a minute. Okay, that's what's going on here, moles to grams. And then up here, what we did was we took moles of compound to moles of element, of a specific element, right? That's what we did here. We took the compounds that were given, right? And we used those with a little bit of stoichiometry. This is the stoichiometry, by the way. Stoich. The mole ratio to determine how much of a specific element is found in those compounds. Okay, now why is that important? Well, we're going to get to that right now. Given that I have 0.02368 moles of carbon, okay, I'm going to convert that to grams, and you'll see why in just a minute. I know that 1 mole of carbon is equal to 12.01 grams of carbon. Okay, so 0.02368, okay, times 12.01, that gives me 0.2833532 grams of carbon. That's where I'm at right now, okay? 0.283532 grams of carbon. In the last example, I think I flipped these two numbers, the 3 and the 6. That's why I was getting a weird result. Okay, that's why I wanted to take it nice and slow. All right, let's go with hydrogen. Hydrogen has 0.070688 moles of hydrogen. And I'm going to take those to grams. Okay. I know that 1 mole of hydrogen, right, and this is the atomic mass now, okay? 1 mole of hydrogen has an atomic mass of 1.008 grams hydrogen, okay? Make sure to cancel these out here and here, all right? So 0.070688 times 1.008, that's going to give me 0.071254 grams of hydrogen. All right, now listen, this is a video, so feel free to pause, rewind, rewatch whatever part you need to, okay? Now, the reason we needed to figure out grams, okay, and this is why. I'm going to scroll this up a little bit, okay? We were giving a mass at the beginning, okay? We're saying that the sample had a mass of let me see, there's the question here. Let's scroll down, of 0.5438 grams, okay? So 0.5438 grams is the mass of the sample. Okay, that's the mass of the sample. So here's what it's telling you, is you had a sample that is 0.5438 grams. Now we just figured out that of 0.5438 grams, okay, of those, 0.32 grams of that equals carbon, and 0.071254 grams equals hydrogen, right? So of the total sample of the mass, right, that we have, these are the amounts that are attributed to carbon, and this is the amount attributed to hydrogen. So knowing that our compound has carbon, hydrogen, and oxygen, we just figured out that these two guys occupy, right? The total is equal to 0.5438 grams, right? 0.283532 plus 0.071254, right? These guys take up 0.354786 grams of the total, right? So if I wanted to figure out how much of that was oxygen, well, that's simple, right? I would take the total mass, right? Total. And then I would subtract 0.354786. I would subtract the total mass of carbon plus hydrogen. So 0.5438 equals, minus 0.354786. Hope I got that right. You would end up with 0.189011 grams oxygen. Okay, does that make sense? So what we did was we figured out how much of the compound is carbon, how much is hydrogen. We added them together, and from there we were able to determine that we have, of the total sample, 0.189011 grams of oxygen, right? So why does that matter? Well, it matters because now we know that we need to get the empirical formula, we have to figure out how many moles of hydrogen are present. And here's how you do it, right? Now we're going to take the moles that we just gathered, okay? Go to oxygen here. And we figured out that we have 0.189011 grams of oxygen, okay? And I know that in 1 mole of oxygen, there are 15.999 grams of oxygen. 0.11 divided by 15.999. I end up with 0.011814 moles of oxygen. Okay, so that's where we're at. That's where we're at. So now we have the moles of carbon, right? We have the moles of hydrogen, and now we have the moles of oxygen. So here's where we stand. Here's where we stand. Carbon. Now the lucky thing is we already have these numbers. 0.023608. 0.02368. Hydrogen is 0.070688. Okay, and oxygen is 0.011814 moles of oxygen. So now it just becomes a simple empirical formula. Everything that we did above, that's all the stoichiometry part. The empirical formula begins now, right? So now we got to do is we got to divide by the smallest quantity. In this case, it's going to be this guy right here. Okay, 0.011814, 0.011814, 0.011814. All right. Let's figure out what we get to. 0.023608 divided by 0.011814. Here's where I end up. Carbon ends up at 1.99831. 0.070688 divided by 0.011814. Hydrogen ends up at 5.98341. Okay, and oxygen obviously ends up at 1. Okay, now these numbers are close enough, right, that we can round. We can round this. So our empirical formula based on our work is going to be C2H6O1. C2H6O1. Okay, that is the empirical formula for the compound that was burned. Okay, take a minute, pause it, catch yourself up, and then we're going to start the molecular formula. Now, to get the molecular formula, we first have to find the molar mass of the empirical formula. This part's easy, don't worry, of the empirical formula. Okay, so the molar mass is C is equal to 12.01 times 2. Hydrogen is equal to 1.008 times 6. And oxygen is equal to 15.999 times 1. Okay, so we're multiplying by 2 because there's 2. We're multiplying by 6 because there's 6. And we're multiplying by 1 because there's 1. So let's get that going. 12.01 times 2. That gives me 24.02 grams per mole. Okay. 1.008 times 6. That gives me 6.048 grams per mole. Okay, and then obviously this doesn't change. That gives me 15.999 grams per mole. If I add all these guys up, plus hydrogen, plus oxygen, okay, I end up with 46.067 grams per mole. Grams per mole. Okay, so empirical formula, molar mass, okay, is going to be divided by the molecular formula, molar mass. Okay, and what that does is going to tell us a ratio. It's going to tell us by how much the empirical formula was reduced. So the empirical formula molar mass is here. We just found that. Okay, so we're going to use that one, and we're going to say that's 46.067 grams per mole. Okay, we're going to divide that by the molar mass given to us. Yes, that molar mass is in the question. Let's scroll up. Look at all this work. Right here, 138.144 grams per mole. So that molar mass is the molar mass of the molecular formula, grams per mole. Right? Sorry. Flip this. I got too caught up. 138.144 grams per mole divided by 46.067. Apologies. Okay. So 138.144 divided by 46.067. Okay. That's going to give you 2.99876, which rounds up to 3. Rounds up to 3. Okay? So one more time, apologize. It's molecular. Let me abbreviate this a little bit. It's going to be molecular formula, molar mass, divided by empirical formula, molar mass. Okay, and that's going to give you this ratio. Basically, what that's telling you is that the molecular formula was reduced by a factor of 3 to get down to the empirical formula. So once we have this ratio, then all we got to do is multiply the empirical formula by this quantity, C2H6O1, right? You don't have to write the 1. And this 3 basically just distributes, right? Just like in algebra. Therefore, the molecular formula is going to be C6H18O3. And there's your answer. The molecular formula C6H18O3, and your empirical formula is C2H6O1, right? Now, can you see how if I have the molecular formula, how the empirical formula is just the reduced version of that to the simplest whole number ratio, right? You reduce it and you get to the point where you cannot reduce. Cannot reduce. That is your empirical formula. Okay? All right. So I know it's a lot of work, and I told you guys that this was going to be a lot of work, but hopefully this kind of helps it make a little bit more sense. All right? Please feel free to rewatch the video, pause it, rewind it, fast forward, do whatever you need, and hopefully we can make heads and tails of this, okay? All right, guys. I wasn't going to rest until I got this problem to you guys, so there it is.